at Asia, I think we get an even more shocking look. Look at that. This is 1 meter of sea level rise. Look at the delta, the coast of China. Particularly look at Indonesia and the islands of the Pacific. So one major issue that nobody can avoid is the sea level is rising. It's rising pretty steadily at about 3 millimeters a year. It's likely to increase pretty radically, and we just know that from the behavior of land, glaciers, and ice sheets. So Dr. James Hansen, who gave a talk here just the other day, he's looked at the Antarctic. And what you have in the Antarctic is a land sheet that's being undercut by warm ocean water generated by the warmer ocean. They have what they call retrograde valleys. So these are valleys that 119,000 years ago, we know that the warm water in that particular interglacial, very similar to our current one, it got into the West Pine Island Glacier underneath it and caused about 4 meters of sea level rise in about 40 years. Dr. Hansen thinks of that as a real possibility and is proposing that we get down there and find out that. So let's take a look at 4 meters. Here's 2 meters, 3 meters, 4 meters, 5 meters. Look at the coast of China, look at southern Vietnam, look at Bangladesh. So it isn't just the island nations that we've got to worry about. Sea level rise is a huge issue for us right now. We don't know what's going to happen. I've been working with some people in the U.S. to try to organize a better look at the Pine Island situation. So we can look around the earth at Europe, Africa, the Americas. Pretty huge issue just from sea level rise. So here's the culprit. This is carbon dioxide and carbon monoxide. The white stuff is carbon monoxide. And we're starting in winter. And we'll just bring it down so we're looking at the Northern Hemisphere. So the red stuff you see moving is carbon dioxide moving with the weather. So what you'll see is that it seems to be increasing. Here is February 25th, 2006, and we get into March and so on. It seems to be more and more CO2. So what's happening here is during the entire Northern Hemisphere winter, all the leaves and crops and so on that are fallow are basically decaying and putting carbon dioxide into the air. So look at that unbelievable amount of CO2. So if that's how it's working, what do you think happens when it gets into summer? What happens is the leaves come onto the northern boreal forests and they pull out the carbon dioxide, and I'm going to speed it up a little, we'll just see that, and voila, the CO2 disappears. It's nowhere near as strong. So this is just the annual breathing cycle of the planet. NASA, who created this, did a very interesting thing. They basically went through the whole year, and they have a little color table that's very sensitive. These areas of red are, at this particular year, back in 2006, they are able to show the difference over 1 year of the human input of carbon dioxide. So here we are in September. Northern Hemisphere still looking pretty low on carbon dioxide. If we speed it up a little, here's October, here's November, and here's December. So where are we here? Where we are is we've gone through the whole annual cycle. The leaves have now decayed and put carbon dioxide into the air. And the question is, how much did the people put in? So I'm going to show you. I'm just going to move it to the beginning of the year. Look at the difference. That difference in the red is the amount of carbon dioxide humans put in 1 year. So we're not just this little species that's coexisting without changing anything on the planet. We are making big changes. And of course the key to carbon dioxide is, if you look on the bands, it's basically an absorber. So it takes radiation from the surface of the earth, and we all radiate, and instead of letting it go out to space, it throws it right back to the ground, and that's the problem that we're facing. We have to look at the geophysical system. We're a planet that's ocean dominated, about 70% ocean. This beautiful image are ocean currents colored by temperature. So this green stuff, this is what's called the Humboldt current. It comes up to the equator, and some of the water's carried west. There's something called the equatorial countercurrent. And as that water goes across the Pacific, you notice the Pacific really covers half the globe, this giant ocean. And it gets into the western Pacific, and it's very warm. But notice something also. Part of it streams down into the Indian Ocean, and part of it goes north. So the ocean is circulating. You can take a drop of ocean water, and in 1,000 years, it'll go through every ocean basin. So the ocean is our big integrator for the planet. It's moving around, and it's really been our savior. I did a calculation which was published that said, okay, suppose that we hadn't had the ocean taking all of our heat. How much warmer, if the ocean hadn't absorbed all the global warming heat, how much warmer would we be? The answer is the entire atmosphere would be 30 degrees Celsius warmer than today if the ocean hadn't taken the heat. 60 degrees Fahrenheit, the whole thing, we'd all be frying. So the ocean is taking the hit for us, but it has a long memory. We look at the ocean currents, we see that they are really complicated, but they're exchanging heat. They're bringing the cold water from the north and the warm water from the south. So there's another aspect of the global ocean. This is actually, in terms of my view, I think part of the reason for creation of Science on a Sphere is how beautiful the geophysical planet is. We do Mars and the other planets. What we're looking at here is sea surface salinity, the amount of salt in the water. Now, salt is more dense than water, so when you get a very salty ocean, it changes the density. And if we look up north, we see that it's very dry and salty here in the subtropics. The reason is those are the ocean deserts. It doesn't rain much. And what happens is this dense water is carried northward. Right here is where the Titanic met its demise. It's the blue stuff is fresh water coming down from the Arctic, carrying icebergs. And there's the Gulf Stream, the meridional overturning circulation bringing warm water to Europe, which is why it has such a relatively benign warm winter. We go into the Pacific, we see the big equatorial current. These are called Kelvin-Helmholtz waves, these little shear waves. And when we get over to the West Pacific, we see a very fresh water. And this fresh water is something that anybody who's ever been in the West Pacific, Singapore, for example, or Borneo, it rains incredibly. And so it's really the fresh water due to the rains that keeps that so, the rain keeps it so fresh. We're going to move on now to the atmosphere. So we kind of have the geophysical ocean. It's circulating stuff around. It's absorbing most of the heat. It's also absorbing a lot of the carbon dioxide. Here we're looking at four different aerosols. So aerosols are little dust kind of things in the atmosphere. One of them is sea salt. So sea salt gets lifted up from the ocean, and a really great place to look at sea salt is down at the South Pole. So if you all at once decide that you're going to take your little boat and circumnavigate the world, and you go down into the roaring 40s and the roaring 50s, you'll see these incredible storms, and they're pulling sea salt off the ocean and depositing it onto Antarctica. So that's sea salt. Let's look at some other aerosols. One that's really amazing is look at the Sahara Desert and the dust, that orange stuff that it generates. You watch this for a while. It comes all the way across to the Americas. The American gardeners in the eastern United States, when they put a spade full of soil, it's got a lot of Sahara dust in it. We didn't really realize this until the satellite era, and it really affects hurricanes and everything else. We have another one, black and organic carbon. So these are coming off of plants. And when we look at Africa, down here we see the green stuff coming off the jungles of Africa. And we're also getting a little look at this white thing. This is actually sulfates. So we get sulfates from a couple places. One of them is, if you've ever been to Yellowstone Park or Iceland, you smell this sulfur smell. Those are sulfates. And that's a little volcano in Africa doing these sulfates. So let's just take a look at sulfates from another source, and that's burning coal. So if you're burning coal, you generate sulfates. And we see here in China and Asia, there's a pretty good amount of sulfates being created, as there are in the United States and in Europe also. So if we just bring it down, you see Europe is generating a pretty goodly amount. So sulfates are created by volcanoes and they're created by people. I'm going to give you a little special treat, which is you watch right here, right off of the African coast. We're going to see a volcano go off. See that? So this is the sulfates from the volcano. And if you look in the paleo history, there have been giant volcanoes in the world now. We remember Pinatubo in 1992, which cooled us 2 degrees Celsius the following winter. Tambora actually caused snow in Western Europe and in Eastern America in July. So these can affect weather globally. I'm now going to show you 2 of the major effects due to climate change. One of them is ocean acidity. And we're looking here at 1868. You can think of this blue area as the area where the shellfish and the corals are happy. They're happy because this thing called aragonite is a calcium carbonate, and blue means it's plenty available to build your shell if you're a shellfish. If we get down here into the oranges and the red, it means you're in big trouble. As you try and build your shell, you basically are continually dissolving. So when we humans put carbon dioxide into the atmosphere, we're really getting it into the ocean. And I'm going to go through a fairly quick look. We're now 1915, and we come all the way up to today. And particularly if we look at high latitudes, we see we're beginning to get a lot of orange. That's because cold water absorbs more carbon dioxide. And if we follow this through to the rest of the century, we see there's a huge negative change in the global ocean. These red areas here, which are practically covering all of our major Northern Hemisphere fisheries, these red areas, a little shellfish can't even exist. It'll dissolve, it'll get corroded away immediately. So people don't just think of global warming as climate change, think also of the incredible effects on corals and shellfish that we would get. We'll now take a quick look at global warming. We're looking here at the AR5 models, and we're going on the RCP 8.5 scenario. That's 8.5 watts business as usual scenario. We notice as the years go on, 2030, the CO2 increases. We're comparing the temperature to the mid-range estimate of the 20th century. So those red areas are areas where it's warmer. And here by the 2040s, you see how incredibly warm the Arctic is getting. It's as much as 4 degrees Celsius or 8 degrees Fahrenheit warmer by mid-century. And as the century moves on, we see that we end up with the continents roughly 8 or 10 degrees Fahrenheit warmer, 5 degrees Celsius warmer. And that's something that we've learned in recent years, is that the Northern Hemisphere continents are going to warm significantly more than what you hear about the global average. The oceans are not warming as much. As we look down in the Southern Hemisphere, we see that where the people live and where they're trying to grow their crops, this is a hot, dry, hostile to agricultural world. So our fisheries and our agriculture are pretty threatened. I have one last image I'm going to show you. This is air traffic over the world on a 24-hour cycle. If we look in East Asia, we see the planes flying from Hong Kong and Tokyo and the major cities. Each little dot is a commercial aircraft. And you can see this is 12 noon in East Asia. So when we come over to Europe, we see a real hotbed as the sun rises and the planes are flying. And shortly here we'll see a big phalanx of planes head across the Atlantic toward the United States. And we are a global conference. We're an industrial civilization. We're here because we were able to fly here. We're not going to turn back from our industry. We have to find a way to have our technological industrial civilization without putting these polluting gases like carbon dioxide into the air. That's the job we've got at COP21. Here comes the planes along the highway to the U.S. And when we look at the U.S., it, of course, is a hotbed of activity. So my summary is, we're not turning back. We're 7 billion people headed toward 9 or 10 billion people. We need industry and technology to solve this problem. The solution is undoubtedly going to be an energy economy that doesn't put out anywhere near as much CO2. It's our job here to hope that we can help make that happen. So thank you everybody for your attention.